Started. Hey, how's everyone? Whoa, that was loud. How's everyone doing? Feeling good? Feeling good? Conference is coming along pretty nicely, huh? This is really fun to be part of. I'm Andrew Ritz. I'm a dev manager at Microsoft. I run core networking for Windows. And welcome to Networking for Connected Standby. So you've been hearing about Connected Standby really all week. This new mode we've got, new opportunities, really a real chance to reimagine how different applications can work. We're going to spend a little bit of time today talking about what Connected Standby is, and we're going to spend some time really framing the problem. What does the Connected Standby opportunity look like? And then really what the focus of the talk is to really drill into what does it really mean for the networking to participate in Connected Standby. Now, for good measure, I'm going to talk about one topic that's not quite related to Connected Standby, and that has to do with optimizing power when the screen is on. But the key is when you come out of here today, you're going to know how to go off and design network devices for Connected Standby and understand really how we've worked hard in Windows 8 to make it easy, just really easy, for networking devices to save power, because we focused on this an awful lot. So it's pretty simple. What's the story? The network's always connected in Connected Standby. Pretty simple statement. It's really kind of, when you think about it, it brings just all these opportunities, these new user experiences, very intuitive user experiences for people. And that's really the exciting thing, that I'm here to tell you about today. You're going to hear about opportunities for application developers, and you've been seeing Windows today, and over the last couple days, how fluid and up-to-date and alive it feels when you go to those menus and you're seeing toast notifications and tiles being updated. If the network's always connected, that stuff can always be there. Your machine is fresh and alive, and it just feels right to end users. Now, along with that, there's a set of challenges that come, specific to networking to make this work. And I'm here to ask for your help if you're making network devices to understand what you have to do to make this experience come together. That's just going to really knock the socks off of our customers. So let's just spend a little bit of time talking about Connected Standby and kind of recap, hopefully, what you've already heard. Just a quick show of hands in the room. How many people were able to see Pat Steeman's talk the other day, Understanding Connected Standby? I'd say that's probably a good third of the room or so got to see it. I know there were a lot of people that were stuck outside. Everyone crammed in close quarters, but Connected Standby is a new state in Windows. This is all about low power, very energy efficient systems. When you have a very energy efficient system that can be always on and have very low idle energy, it really brings together this really new experience. And for applications, again, as I was saying, it's all about applications being alive and up to date and really removing latency out of the equation. Latency is just something you don't really have to worry about anymore with Connected Standby. So really, how do I think about Connected Standby? It's kind of like turning the screen off. And, I thought Pat did a great job kind of saying it's a lot like, a cell phone. When you turn a cell phone on and off, it's always running. He had that nice graph, if you go back and look at his talk, about when you're in standby, you got this very level power. And when you're in Connected Standby on a cell phone, when you took his trace, you can see that there are little spikes of activity, and the system is actually running. So the cool thing in Connected Standby, Network Adapter is maintaining that connection to the network, and the system is running. And Metro-style apps can continue to receive live tile updates and toast notifications. And now I'm going to spend a little bit of time. You didn't hear about as much of this in the other talks, but we're going to talk a little bit today about background tasks and also these things called push notifications. And those are going to enable customers to receive real-time communication notifications from apps like an email application, instant messenger application, VoIP application, things like that. And you can imagine your screen is off and you're able to get those things. It's a really powerful opportunity and something we're really excited about, people trying out our APIs, our new Windows Runtime APIs, and seeing how, if you can imagine this experience with us. So let me talk about some of the challenges in networking today and why it's not so easy to just snap your finger and have the Connected Standby experience with today's networks and today's network devices. First off, when a machine goes to sleep or hibernate, right, the network device turns off. So the problem, obviously, is when you're going to have this delay. You're going to have this latency when resuming. You're reconnecting to an access point or what have you. You're renegotiating your layer 3 IP address. All of those things sort of add latency. Another challenge we have in today's networks is that depending on the network you're on, broadcast network traffic can cause a machine to interrupt frequently during an idle state. And that those frequent interrupts during idle translate to making it really challenging to keep machines in low power states. So we got to do something about all of those interrupts and all that broadcast activity happening on networks. And I'm going to spend some time talking about that challenge in a bit. The third challenge we have is that applications in today's Windows programming model, they can really send and receive network traffic in a somewhat unpredictable manner. I mean, it's really up to the application logic to decide when you're going to do that. And if you think about an app receiving it, it's really up to the server or whatever you're connected to. And because of that causes a challenge as well. And that challenge, has to do around radio management. And in particular, with mobile broadband radios, it's hard to know because you could be having this traffic at any time when to turn that radio down and get into a really low state. And so Windows isn't doing a whole lot to help there and bring any predictability to the problem. So we're going to talk about that as well. So with that framing of connected standby, again, remember, it's this really low power state. Let's kind of delve into some details about how you implement network adapters for this and how it actually all fits together. So in connected standby in Windows 8, what we expect is that network adapters are able to efficiently maintain network connectivity. So imagine that we've got this very low idle, trickle thing, and we're maintaining our connectivity. In the network adapter, it's going to do that sort of autonomously, maintain that layer 2 connectivity. So that means it's maintaining, connection to the access point, and things even below that. But not just that, it's also going to be doing things like an ARP or NS protocol offload when you're in connected standby. A number of offloads that you probably heard about in Drew's talk earlier today about understanding wireless networking in Windows. Now, along with that, Windows is maintaining in connected standby the L3 identity, basically making sure you don't lose your IP address. So, again, when you went into connected standby, the network was connected. When you come out of connected standby, the network is still connected. So you've got that connectivity to the access point on these great mobile form factors that are, have cellular or mobile broadband connectivity or wireless connectivity. And that connectivity is there. You're ready to go. No latency coming in and out. So that system is there. Just as quick as you can light up the display, networking is there. And networking is no longer the critical path because the network adapter has maintained this connectivity, and we've maintained sort of the identity. So that's sort of one piece of connected standby. Now let's talk about this push notification concept that I was talking about. This is pretty cool. I'm really, really excited about kind of the experience that this brings for end users. So we've imagined that a set of Metro-style real-time communication apps can receive push notifications in connected standby mode. So the way this works is that the RTC app is going to make a connection to its server. It sort of makes sense. You're going to make your TCP connection to a server, and then you're going to use these new RTC trigger APIs. They're part of the Windows runtime APIs, and you'll use those along with your favorite Windows runtime networking APIs to make your connection. Maybe you saw Dave Thaler's talk a little bit earlier today about the new Windows runtime socket APIs. You could use those APIs to make a connection from the client to the server, and then register that connection via these trigger APIs. Now, once the connection is put together in our design around these, Windows 8 helps to ensure that the network connection to the server isn't dropped. And the way it does that is that we have background tasks that get registered via the trigger APIs, and those allow the client to send a periodic keep alive message to the server so that that connection doesn't get terminated. And you're going to hear a ton about this tomorrow if you come listen to the talk that's really going to dive into these APIs. I just want to make sure you guys understand, as you're thinking about how to build the network adapters, that you understand the application model that goes into this, because it is really powerful and simple at the same time. So what's going to happen? Client has got its connection to a server. You can sort of see in the illustration here. The server is going to send a notification packet to the client when its attention is needed. So you can imagine a server. Imagine I've got an email application. That server is just received a high importance email and says, oh, time to send a push notification to the client. So the server does that and sends something to the email client. That email client then is going to process that packet. And we're going to do this in a very energy efficient way, because you're going to help build these great network adapters that do this. So how does this work? Well, a little bit more framing, just so you don't get confused. Now, most apps, Metro-style applications, they're simply going to use tile and toast updates. And those tile and toast updates are going to make it so that your application and the start menu looks very alive and fluid. And you don't have to write any background processing code to make that happen. Those things are going to get delivered just fine. Now, there are going to be a set of applications, these RTC applications, that are going to use the RTC trigger APIs. And under the hood, what happens is when you use those APIs, we sort of record the IP addresses and sort of a 5-tuple pattern, that we're going to match on from the server to the client. And those wake patterns, though, are a finite resource. And as well, processing background tasks in the background can consume power. And if you remember in Pat's talk, we're always talking about minimizing those windows of activity. So we constrain the number of applications that can use RTC trigger APIs to those on the lock screen to make sure that you have those minimized windows of processing, and also because these wake patterns on the hardware are a finite resource. And you can learn a lot more details about that, but there's, I think we're asking that you have something like 16 wake patterns on the hardware. So what happens when we go into connected standby? Well, a couple things happen. You've been learning about, in the connected standby talk that Pat did, you'd learned a little bit about desktop activity moderator, right? And the whole notion there was that was going to suspend desktop applications. You've already been learning all week about these Metro-style applications. And you know by now that when Metro-style applications are in the background, they're suspended and can't consume any power. Well, when you're in connected standby, all those applications are suspended. But that's not all. Windows goes one step further, and what we do is we start suppressing all of the outbound network traffic in connected standby. So once we've got that outbound traffic sort of suppressed, we arm the NIC for wake using these wake patterns that are, correspond to each of those RTC trigger apps. And then we're going to place the network adapter into a low power state, D2 or D3. It kind of depends on the system bus that you're connected to, which D state you're going to go into. And I'll be talking a little bit about some of the gotchas about that in a little bit. Now, I want to just remind you, this is a little bit different than your traditional wake on LAN. We're not putting the machine into standby or S3 state. Windows is maintaining context and memory and is able to continue to execute. We're doing sort of a runtime low power state in the network adapter. Does that make sense? Runtime low power state. So continuing on a little bit further, remember we were saying in our sort of fictional story there, we had that email application that got the push notification from the server. So when a waking pattern comes in and is received by the network adapter, it's going to wake out of that low power D2 or D3 state, go back into D0, and deliver that packet up to Windows. And then Windows is going to trigger a background task in the RTC app to process that received packet. So that's going to be application logic that got invoked via this push notification. Again, we're going to dive into all those details in the talk tomorrow about how that works. Other important thing here is that the device is in this low power state, sort of armed to only recognize those pre-configured wake patterns. And so that means that all other incoming packets are dropped. So again, when you think about that low idle power, the network adapter is maintaining your layer 2 connectivity Windows has suppressed all of the outbound activity, and only the inbound activity that gets processed are those corresponding to these push notifications. And so what that means is very low idle power and a pretty cool user model, as you're going to see in a little bit. Let me talk about a couple of kind of gotchas, some things you need to know to make sure that this connected standby thing kind of gets concrete in your head. So one particularly interesting thing is that on some low-power buses, for example, SDIO bus, you may require a sideband GPIO network wake signal. And this is really important to improve energy efficiency in connected standby. The idea in these integrated devices is that we even want to turn off the SDIO controller itself, not just put that network adapter in the low power state. And so by doing that, you can have a very small power domain that needs to be powered up, waiting for that notification to come in. Another thing you need to think about in your network adapter is that the timeliness of exiting out of this D2 or D3 state, depending on your bus type, needs to be fairly timely. It needs to be quick. We're talking about real-time communication apps. A VoIP call is coming in, and that phone needs to ring, and so that device needs to wake up very quickly. I think about this. I say very quickly. It's a kind of a vague term. I'm thinking in tens of milliseconds, probably a cap of 100 milliseconds, somewhere around there. That's a great conversation to have with you guys. We'd love to hear what you think is reasonable to be implemented in the network adapter. But to make the application model work properly, 100 milliseconds is probably getting up towards the upper edge of what we want to make that transition. Another thing I've been stressing is that we want to minimize those intervals when we have spikes of activity processing background tasks. Well, to do that, it really depends on infrequent push notifications. So some care needs to go into the design of your push application and that server, so that that server isn't just pelting the client with push notifications every couple seconds. If it does that, then the idle power is going to go up and your battery life is going to go down. So, in my mind, to calibrate it, I think of push notifications maybe coming every couple of minutes, maybe every 15 minutes, something like that is, sort of the model we think of. One other thing I want to make sure you're aware of is that wake pattern matching may not be the only reason for the network device to wake. For example, one thing that can cause the network to wake is that you came into a connection with a hotspot. Maybe you actually didn't have network connectivity. You just have a Wi-Fi device and it wasn't near an access point. But when you got into range, we have the ability to automatically connect to networks. And you heard about that in Drew's talk. So what's going to happen there is actually a really cool kind of little mechanism. The way this works is that the connection to the network can cause a background task to get run in the RTC application. And that RTC application can then initiate a connection back to its server and sort of restart this whole cycle of life, where it's going to connect back to the server, register itself, hey, start sending me push notifications, and that whole flow gets set up again. So you just came into range. The user didn't have to interact or relaunch the app or anything like that. And that can cause the network adapter to come out of a low power state as well. So I know I threw a lot of stuff at you there. We're going to walk through a demonstration of this. And we're going to do this on NVIDIA Tegra development platform. So many thanks to NVIDIA for pulling this together. And hopefully, by talking through this one more time and showing the demonstration of the application, it's going to become really concrete to you how the app works. We maybe need to adjust this a little here.
It's kind of distorted.
It doesn't look like it is up to date at all, like the Wolf Vision is.
Try to switch away and come back. Which one were you on before?
Yeah, we can try that.
Were you on PPT?
So we're having a problem with the Wolf Vision.
PPT?
Sure. You're pressing on the wrong one, but you got to go down to this one here.
Okay.
So let's try switching back and see if the Wolf Vision decides to cooperate. Well, isn't that fantastic? Let me see if I just do...
I think we had something.
Well, it's starting to come back to life, but still not. Well, he's working that out. Let me tell you a little bit about the application. So what we did is we wrote a little chat application. Is this working now? So I guess it's not tracking the mouse, so it's still not quite working. We wrote a little chat application. This chat application was written in C# and in XAML, and you know, very simple application that we're going to use to demonstrate how to use the RTC trigger APIs. It's still not tracking. This is pretty exciting, huh? Ready to do your demo, and then the projector is acting flaky. But what we'll do is we'll have you come single file through here and look over the screen. How about that? Ari, you are a lifesaver. All right, so this is our simple little chat application. And like I was saying, C# chat application, it's using those Windows Runtime Socket APIs, and it's going to make a connection from a client to a server. We have another client over here that Mahender's at, and these clients can send messages back and forth to each other. They send the message to the server relays the connection to the client. So you want to send a message to me and come and demonstrate this? All right, so what happened here was we had a little toast come in. So hey, crowd, awesome, Wolf Vision is working. So this thing is in the foreground, nothing too exciting going on right now besides just a simple chat application. But as I was saying, in the Metro-style application model, when apps go into the background, apps get suspended. So you can see our little Ping Me app here, and in a moment, you're going to see that right there, it's suspended. So at this point in time, the application can't run any code at all. Or maybe not. So what happened there was that we received a push notification while the app was suspended. And when that push notification came in, even though the screen was on, we're not talking about connected standby yet, but even though the screen was on, that app was suspended, we were able to run that background task. And that background task popped up that little toast that you saw. We clicked on that, and it switched to the UI portion of the application. Those background tasks, they're not allowed to interact with user interface at all. It's kind of one of the things that's special about background tasks and the application model is that they run in this very constrained sort of sandbox. So yeah, you know, that's sort of the demonstration I guess I wanted to show you. So we should probably get back to the rest of the talk.
Aren't you forgetting something?
Oh, that's right. I forgot. Yeah, so we got to show connected standby. So as you can see there, this sort of illustrates sort of the concept we have here, is that the screen was turned off, and you know I put the machine into connected standby right there, and still a bit of work to do in the network adapter to make sure the network adapter is going into that low power state. But what happened was that the application was able to receive that notification, and it did this thing that we call a ringing toast. So the idea there was that it could alert the user, hey, something's going on. You could imagine, all sorts of possibilities there. Alerting the user that a VoIP call is coming in, and telling the user take your device out of your bag or whatever, and attend to it. I turned the screen on. You can see the toast was there. Again, that sort of same flow. It would bring that application into the foreground if it weren't there already. So that's just something to kind of give you an idea of how these RTC trigger APIs can be used to build some really neat user experiences that are very respectful of battery, going to give a long battery life, and something that we think end users are really going to appreciate. So let me roll forward a little bit, and let's talk about how to deal with interrupts from broadcast traffic. This was something that I had mentioned earlier on as one of the challenges, something we needed to deal with. Now, it ends up that broadcasts occur frequently on many types of networks. The packet delivery timing is unpredictable with broadcasts as well. Now, most networks have this type of behavior. We look in corporate networks, we look in home networks, we look in public networks. In fact, we had this awesome project. This guy was going around to different coffee shops and capturing broadcast activity. We went to airports to see what kind of broadcast activity was going on. We went to our library to see the broadcast activity. Wherever we looked, we saw broadcast activity, and those correspond to each broadcast packet can often generate an interrupt, which requires system processing. And that's going to lead to poor energy efficiency on the system. In fact, on corporate networks, this just blew me away when I saw this, but we were seeing broadcast packets up to every 20 milliseconds on a corporate network. I mean, it's just stunning when you think about that, and you think about, I always thought in my head of graphics and a vertical blanking interrupt, 1 every 60th of a second or whatever it is, as being a very high frequency thing. But it ends up that network broadcast activity is way up there as well, and something that we have to do something about. Now, what's interesting about broadcast activity is that it ends up that few packets actually require a complex response. A lot of them can be discarded, and only some of them, it ends up or actually require some big response. So, with that in mind, we set out to come up with a solution for Windows 8 that's going to help address this broadcast activity. So what we do is we program filters on the network adapter to recognize what we call these noisy broadcast patterns. And when I'm talking about a broadcast traffic, we're talking about ARP, we're talking about LLMNR, neighbor discovery, SSDP. There's all sorts of patterns out there that you may run into. Now, the nice thing about these filters that we define is that they're really simple to implement on the NIC. This doesn't require any deep packet inspection or anything like that. It's really just matching, up to like a port number or something like that. It's, very straightforward filter to implement, and analogous in a lot of ways to those wake patterns that we were talking about in connected standby. In this case, though, we're talking about the system being on, screen is on, we're interacting with it, and we're programming these filters. So what happens with these filters is once the network hardware matches the broadcast filter, when the screen is on, what it's going to do is that network hardware needs to locally buffer the packets for later processing. And we illustrate that sort of in this diagram here to show that the CPU won't be interrupted by traffic during this batching interval, and that's going to lower the power consumption by allowing the rest of the platform to be in a very low power state. Now, along with this, Windows 8 is going to process these batches of these coalesced packets in one pass, and we can do that in a way that won't break any of the protocols. So, for example, LLMNR, which is a protocol around name resolution, requires a timeout of somewhere around 300 to 500 milliseconds in order to remain protocol compliant. So we program this filter and tell the device to interrupt us no later than that time. And so we go from perhaps an interrupt every 20 milliseconds to an interrupt every 500 milliseconds, efficiently process these packets and get back down into a low power state. And because we can discard a lot of those very easily, it's one of those things where we're minimizing the interval where we're actually actively processing packets. So just want to touch on that real quick. A lot of great documentation and information for you to learn about that up on our website. So let's talk about one sort of final topic I wanted to go through, and that's low-power mobile broadband. So there's a couple challenges around mobile broadband radios today. One of the sort of challenges, or I guess truisms, it's just one of those things that is that mobile broadband radios stay in a high power state after transmitting data. And that's for good reasons. The chances really go up that another transmission is going to happen in the near future. If you sent one packet, there's a really good chance you're going to send another packet. That's always sort of been the case. And the other thing to keep in mind is that there's an opportunity cost to turning radios down, turning them back up, turning them down, turning them back up. And if you did that frequently, that's actually going to cost you some power rather than staying in the high power state. The other thing to keep in mind is that frequent transitions can negatively impact the network infrastructure, like your cellular towers. So you need to be mindful about when you go into these low power states. Now, in today's systems, the mobile broadband device decides when to change states and to go into make one of these radio transitions. However, the devices are effectively forced to guess and negotiate when to step down to low power state today because Windows isn't giving any hints. So, introducing in Windows 8, we've got OS-assisted fast dormancy. So the idea here with OS-assisted fast dormancy is that Windows, remember, we're going to put the system into a mode, this connected standby mode, where the network's going to be quiet. All that outbound network activity has been suppressed. And inbound activity is limited to low-frequency push notifications. So those aren't happening very often. Quite simply, Windows provides a simple OID, an OID hint, to the mobile broadband driver to indicate that the network is going to be quiet. And the mobile broadband device can then aggressively enter into fast dormancy state when that happens. Let me illustrate this with a little graph. I think it'll make good sense to you. So this is a trace that we took on a system. And you can see what happened here was that we had one small little packet that we received. And we're up in this sort of high-frequency data exchange mode. We're consuming many milliwatts of power. And you can see then that we eventually dropped down to this FACH state, right? And then ultimately, several seconds later, got down back into that low power state. So you can see there's that big sort of area under curve, which effectively translates to wasted energy if we knew that there wasn't going to be any network activity. So, as you might expect, when we know we're done transmitting, when we know we're going into connected standby, we'll send that fast dormancy hint, allow the device to go down into a low power state, and save all that area under curve that could have been is basically wasted energy. So great opportunity there. And with efficiencies in mobile broadband devices, we think you can get to a very low power state very efficiently. So let me just recap. Connected standby experiences are really going to be valued by customers. The network's always connected, and it makes apps come alive. This whole idea around RTC applications or your tile and toasts always being there, your email is up to date, it's going to be just a very pleasurable experience that I personally can't wait to start using. Keep in mind that Windows 8 has several improvements that we put in place that reduce the power requirements associated with network adapters and let us do connected standby. Remember, those network adapters are going to sort of efficiently enable us to have that continuous connectivity. And by implementing this wake capability and runtime wake capability, you're going to enable applications to receive push notifications and to have this really reimagined, very interactive experience with the system. The other innovation that we need to see is around reducing the number of interrupts generated by broadcast traffic. And again, this was when the screen was on that we had to deal with that broadcast traffic. The broadcast traffic, remember, in connected standby, we're dropping everything except for those particular wake patterns that came in. So we talked a little bit about this runtime or D0 mechanism for coalescing that broadcast traffic and bringing down the power consumption there. And finally, a nice hint and for mobile broadband to get into fast dormancy sooner. A connected standby is going to require networking hardware that includes all of these enhanced processing capabilities. So the networking hardware that was present in Windows 7 and the networking hardware that's present in Windows 8 machines that support connected standby are going to look quite a bit different. Hopefully you've got a good idea from this talk now some of the changes that need to happen and need to be implemented in the network hardware to really pull together this cool experience. I want to just highlight a couple of the related sessions. A lot of these have happened already. It'd be great for you to go back and review these if you haven't already, to get a really good, crisp understanding in your head about Wi-Fi networking in Windows 8 and what connected standby is all about. Pat had a nice demonstration there, that you could kind of see the low power, of the system. And finally, tomorrow, there's the application session that tells people how to write real-time communication apps. And I highly encourage, if you're interested in writing one of those apps, to attend that talk and check it out. So I'd be glad to take any questions now. Do you mind using the microphone, if possible? Sorry about that. Sure.
So the NIC is supposed to store all matching packets for, say, 300 milliseconds, and then interrupt the OS.
Yeah, so the question was, what is the network adapter supposed to do when it's buffering these packets? And the idea is that if a packet matched one of these patterns, that it needs to be cached, probably in some sort of local memory, because we can't have any DMA activity or anything like that going to the main system RAM and causing the rest of the chip to light up. So it's got to buffer those locally, and then when a timer goes off, it's going to deliver, and indicate up, a few dozen packets or whatever happened in that interval. Yeah, there's a mechanism in the question was about overflow. How does that work? Yeah, there's a way for you to interrupt if there's a chance that you're going to lose a packet. Great. Question over there.
Do you discriminate between a wired and a wireless connection?
So the question is, do we discriminate about between wired and wireless?
Right. The primary reason I ask this is because there are some of the layer 2 and layer 3 switches which will power down if the wired connection devices, on the other hand, doesn't have a lot of activity.
Well, really, what we've been thinking about in connected standby is really mobile experiences for the most part. We've really been thinking about a device that you're moving around, a laptop, something of that nature. And so we've really been focusing on wireless experiences, mobile broadband experiences, that sort of thing. This notion, though, that you could be plugged in to a wired connection, is something that's certainly supported and abstracted away from the application model if you're writing an RTC application that's going to be triggered. Now, it does probably end up, though, that when you're plugged in to a wired connection, there's a really good chance that you're going to be on AC power or something like that. So, that's a consideration that would have to be made sort of in the overall usage model.
Not necessarily AC power. One of the possibilities is power over Ethernet, right? There's some devices like that. Okay, now focusing on purely on wireless situations, you guys planning to work with particularly wireless module maker? Because a lot of these module maker right now sort of get stuck into the ACPI4 spec, and they handle all the power state themselves, and worst case is that they say, I'm already in a standby mode. If you query me, I will wake up and then consume more power. So you're from a system point of view, you're kind of stuck in a situation where you don't know whether you should go query them. Did they actually get into the low power state or not?
I guess if I understand your question properly, you're asking about whether or not we know that the device is sort of physically actually indicated that, like, it turned the radio off or something like that.
Do they actually go into low power state?
Yeah, for the handshakes to work properly, and from the OS interface point of view, we don't necessarily need to know that. You need to respect the interfaces. That's kind of the key thing to keep in mind. If the device doesn't go into a low power state, though, it's going to mean that the energy efficiency of the system is going to be terrible, right? And you may not have this great battery life experience that Pat was referring to in earlier talks.
This is what we're seeing right now in the actual system design. This is why I think in another session they were talking about maybe a sideband channel to do management to go and probe whether the actual device is going to a low power state or not. Some of the buses may not allow you to do that. Some may. This is something I would actually suggest you guys talk to the actual module maker, make sure they behave properly. Because some of them will fake this state and tell you, say, yeah, I actually went into power state, but they didn't.
Okay, thanks. Other questions? There's a question in the back. Yeah, so the question was whether the apps can program the wake patterns for like the mobile broadband adapter, was that right? Or the wireless adapter? Yeah, so the way, that's really abstracted away from the application. The application that's using these Windows Runtime APIs really just needs to make a connection to the server. And then you'll see, the kind of the coding pattern. It's a very simple coding pattern. It's kind of like saying, I've got a socket, or this connection, and I'm going to use it for the purpose of this RTC trigger. And then Windows, under the covers, understands what that pattern is and takes care of configuring the wake pattern on the adapter. And this is, really, you got to think about these wake patterns being used in a little bit different way. It's, for the purpose of sending a push notification in for a very interactive, application experience. It's not like a traditional wake on LAN that might have been around, a management experience and coming in to do servicing of the system. So it's a little bit different than that. And so, having that facility to program wake patterns really isn't necessary and can be abstracted away and simplified. Just makes the lifting and the application side much simpler. Okay, good question. Okay, yeah. So the question is about when the device is sort of armed for wake and it's in this low power state. When we receive a push notification and it's recognized, how does that flow work a little bit more? Can I drill into some more details? Is the question. So really, the idea there is that once the packet comes in, the device is going to have to locally buffer it. The device is going to perhaps signal some sideband GPIO signal, or whatever it is to the device. It's going to get the controller to wake up. The controller is going to, get that device to indicate that it's no longer in the D2 state or whatever, the D3 state. It's going to transition back up to D0. And when it transitions back up to D0, then that's going to indicate that packet that it has in the system up to the application into Windows. Well, that's sort of how the system design works, right? That GPIO signal is going to come in, and there will be some logic, in the PEP, if you know that term from Pat's talk, that's going to say, oh goodness, this GPIO went off. That means that I need to turn on this particular power plane and get that SDIO controller warmed up and turned on, that sort of thing, and that allows the logic to. What will happen, right? The question is when the packet is received, does the adapter get turned back on? Well, when you indicate this wake pattern, and yes, the adapter is going to transition back from this D2 or D3 state back up to D0 so that it can complete its wake ERP and all that kind of low-level stuff, and then indicate the packet up to Windows for processing. So the question is, if there's multiple adapters, which one do you wake? Well, I think it's the adapter that was armed, is the one that's going to.
Right, simultaneous ABGD, right, 2 different frequency.
I'm not sure I understand.
Right, your
Yeah.
Wi-Fi has 2 bands.
Pat wants to jump in here.
Can I help?
Sure.
Yeah, so the story here is that the system's logically on, just like I said yesterday, and we have facilities to know firmware can describe either through ACPI or through the PEP mapping between something like a GPIO and a device logically. So the system integrator, when he puts the machine together, goes, okay, here's my Wi-Fi device, and it's got a sideband signal, and it's mapped to this GPIO pin, and internally we know, oh, that means I need to power on this driver and this device. All the wake sources, they're all independent. They can all be independently mapped. It's not an S3 transition. So these little intermittent bursts of activity are not a globally coordinated power up the whole machine. They're power up just what you need to get the job done. Is that helpful? Okay, good.
Thanks, Pat.
Yep.
You're my hero. All right, someone else pepper me with a question. So the question is about suppressing outbound activity and how do you get in and out of connected standby. Pat was kind of talking about this yesterday. One of the ways you get into connected standby is that you detect that the user's not present or interacting with the system, and that'll cause a transition. The other obvious way, as you saw here, was like I just pressed the power button and I went into connected standby. And when we do that, we respect the user's wishes. That screen's going off. The machine has to look like it's off. And so in that state, all those affordances that I was mentioning kick in. That desktop activity moderator, suspends the desktop applications. The Metro-style applications are suspended. The network adapter and the networking stack starts to suppress any outbound activity at that point. A question in the back. Yeah, so the question was, if you want to try out this RTC API, how do I go about doing that? Is there some sample codes or something like that to get you started? So we have this application that we've written. We've not published this as sample code yet. It's something we've been thinking about doing, and maybe a discussion we could have offline, about when and what's the right time frame to get that published. This was one that we wrote in C#. By the way, I'm not sure what language preference you would have, but you'll see a lot about the coding pattern tomorrow, and probably a good conversation there. Yeah, so the RTC APIs are projected into C, C++. They're projected into C#, and they're also in JavaScript as well at the moment. Now, there's some challenges with JavaScript and using that to be sort of the back end for a real-time communication app. And for a lot of traditional apps that have been written in the past, they've been written in C++. So, I'm not sure if JavaScript's going to be the perfect answer for this constrained set of real-time communication apps.
Hey, so you said that the wake pattern isn't defined by apps. Where in the system is it defined?
Well, so when you use the RTC trigger API, the way you do that is you sort of indicate your connection that you've established to a server. So it's kind of like you're giving a handle in the API to the trigger API. And Windows can kind of peer into that handle and see, oh, I've got a connection to this particular server IP address. And then that's how the wake pattern is sort of derived. And in fact, that application, that RTC application, think about an email application. It may want to have connections to more than one server. So we allow you to register more than one connection in that RTC app, up to the constraint, some certain constraints that we have in mind for the application. But we can detect those patterns then and take care of kind of doing all that plumbing of the wake stuff and all that, IP, the IP literals and such. If you read about and watch the presentation about the Windows Runtime Socket APIs, you'll see one of the things we really strive to do was simplify the API surface. And you can connect via a string IP literal, but what we think is going to be more natural is that people really use name-based conventions for connecting. So you might not even know, the IP address of your server to configure a wake pattern. And we've tried to make it really, really simple for the application to participate and become an RTC app without even having to worry about some of that logic. Any other questions? Otherwise, if you want to come up front, I'd be glad to take some questions in person as well. Thanks.